All right, all right. I think we're live now. Hello, hello. Hello. All right. We'll get started. And yeah, so ready to learn some probability? Yeah. Let's go. So, so the idea for today is I'll go over combinatorics and probability, and then I'll solve some questions. But if you guys have any, if you guys have any questions, feel free to send it in the chat, or you can just DM me on Instagram. Just like a problem and like answer session, pretty much. All right, we'll wait one more minute. Alright, we'll get started then. So, with combinatorics and probability in general, I think a lot of it, well, at least like combinatorics on its own, I think a lot of it comes down to like the model and how you think. Probability is basically the same thing, except you have a denominator and a numerator. So wait, why is it still untitled? What? There you go. Okay. And I'll share the link in the team so you guys can follow along. Okay, so we'll go over some of the basics first. I'll pull up the formula booklet. So yeah, first thing I guess most important is permutations. So permutations versus combinations, right? Now, permutations, this is where we care about order. So order matters. And in combination, this is where order does not matter. So that's the key thing. So for example, let's say we were to arrange like A and B, then we would have AB and BA. But in combinations, they would be counted as the same thing. So therefore we only have one way to arrange them, which is AB. So permutations, there's a few ways you can see them, usually written. The way IB likes to write it is like N permute R. So you're choosing R from the N people. So let's say you have like a group of N people, and you want to choose, or you have N people in a race, and the first R people gets or get an award. So how many different ways can these awards be distributed? So obviously the R awards are different in this case. So NPR, because the R can be distributed to any of the people, it would be n factorial over or let me just make sure. Should be, yeah, n factorial over n minus r factorial. If you think about this more intuitively with the counting method, this would be n times n minus 1 times n minus 2 all the way to n minus r plus 1. So basically, we're choosing which award to give, right? For the first award, we have n people to give to. For the second award, we have n minus 1 people to give to, because we already gave the award to someone. For the third award, we have n minus 2 people to give to, because we already gave 2 awards to n of the people. So that's why until the r award, where you have n minus r plus 1. Now the difference between combinations, so you'll see combinations written in a few different ways as well. So you can have like NCR. Some places write it like this, NCR, or you can even see it like this. I think this is the way I'm gonna write it because I'm more used to it, but just know that they all mean the same thing. So with NCR, the formula goes like this. It's pretty much NPR, except you have to divide an r squared. So in other words, is n factorial over, other words is n factorial over r factorial times n minus r factorial. Right, so the reason why this is the case is pretty much like the difference between combination and permutation. Why we have to divide that extra r factorial is because we don't care about the order. So let's say we've chosen the r awards from, and we've given them to n of the people. But in this case, the r awards are the same. So we don't really care who gets what award. We just care about which people get the award. So this means that once we've distributed the R awards, let's say we have 3 people, A, B, C, and they, in the first case, they got award 1, 2, 3. In the second case, they get awards 1, 3, 2, or 2, 3, 1, 2, 1, 3, 3, 1, 2, and 3, 2, 1. These are 6 cases that they can receive awards. Let's say there's like other people as well, but we don't care about them. So once we've counted these cases, you see that all 6 of these cases are realistically the same one, right? Because it's still A, B, and C that are getting the awards. That's why we divide by 3 factorial, which is the R in this case. So one thing with combinations that you're going to want to know is that n choose r is equal to n choose n minus r. And there's a bunch of things that you can do with combinatorics, because you can either, explain it in like an actual and intuitive way. Like you can say, for example, I'll do an example with this in just a bit. Like that's one way you can explain with a real life example, or you can show it algebraically. So with this example, let's first explain it intuitively. So let's say we're choosing R people from N people, right? Note that this is the same as choosing the people that we not choose, right? So we're pretty much splitting N people into a group of R and a group of N minus R. In this case, we're splitting a group into N minus R and into a group of R, right? So in this case, we want this group. And in this case, we want this group. But instead, if we just take what's left, these should actually be the exact same cases, right? So once again, these are the same. So this is how you can explain that they are the same using an intuitive way. Now, the other way that we can show it is using algebra. So n choose r we know is n over r factorial over n minus r factorial. And so I'll write it this way. This is n choose r. And write it in front actually. n choose r. Now, n choose n minus r. This is equal to n factorial over n minus r factorial times n minus r factorial. So therefore, this is just n factorial over n minus r factorial. So the first one doesn't change, but this is just r factorial. And therefore, they are the same thing. Right. Next thing I want to talk about is a pretty famous model. It's called stars and bars. So I think we've learned this model in class. I think it's just not called this way. So let's say in a stars and bars model, well, first let's explain distinguishability and indistinguishability. So with combinatorics, there is a very key difference in distinguishable and indistinguishable. So with distinguishable objects, that means that I have like people, right? The people, they're obviously different. The other case is indistinguishable. Let's say I have 5 oranges. Never learned this one properly. I just use putting stuff between gaps. Yeah, that's pretty much the idea behind this. But yeah, I'll just go over this. And you shouldn't be really trying to memorize the formula either, but you should know like how this works intuitively. Because in the end, you're gonna have to create your own model on the test, and it's gonna of course be slightly different than like all the ones you've seen before. So with distinguishable and indistinguishable, so let's say this is like 5 people. So people are of course distinguishable, right? So in this case, we care about the order. And when they're indistinguishable, let's say like 5 oranges. Now this is going to be indistinguishable because, you know, we have 5 oranges. Now for the sake of this problem, let's say that there's not that many, just so it's a bit simpler. But let's say there is 3 people and we have 8 oranges. Now I want to give these oranges to these 3 people. How many ways can I do this? Remember, the people are different, but the oranges are the same. So how can I do this? So the way we want to do this is by looking at stars and bars. So I'll explain stars and bars first. So stars and bars works when you have a group of distinguishable objects and a group of indistinguishable objects, where you're trying to assign the indistinguishable objects to the distinguishable objects, or the other way around. So pretty much the way this works is, let's say we have 8 oranges, which I'll represent using stars. 4, 5, 6, 7, 8. So the 8 oranges are here. Now I want to somehow separate them into 3 groups so that they're given to the 3 people. Now one way I can do it is I can separate it here and separate it here, right? So this would correspond to the case of first person getting 2, second person getting 2, and the third person getting 4. If I were to put it like this, that would be 2, 3, 3. Right? So essentially, we need to put 2 bars into these 8 oranges. So how do we do that? Now you might say, since there are 1, 2, 3, 4, 5, 6, 7 gaps, it's 7 choose 2, right? Like this. But that's actually incorrect because the people can actually get the same amount, or the people can actually receive no oranges, which pretty much means the bars can go on the end. So if the bars were like this, that means the first person gets 0, second person gets all of them, and the last person gets none again. So we can actually put these on the ends. So first of all, we have actually 9 choices to choose from. But also, the lines can go in the same gap. So this would correspond to the case 4, 0, 4. Right? So how can we, separate, how can we count the cases where we have them in the same gap or in different gaps? We don't have to do casework for this one. I'll show you a trick. So the way we want to do it is we want to view the bars and the stars as one thing. And then we essentially have 10 things, correct? And then we're going to choose 2 spots for the bars. So out of the 10 things, or the 10 spots, essentially, we're going to choose 2 of the spots for bars. So this is 10 choose 2. So the way we can distribute 8 oranges to 3 people is 10 choose 2. This is going to be 10 times 9 over 2, which is 45. Right, so one more thing, right? So a small change that I can make is, let's say I still have 3 people and 8 oranges, but now each person, the people wouldn't be happy if one person got all of them and they got none. So each person must get at least 1 orange. So how can we go about solving this question? See, the only difference between this question and this question is the fact that the gaps can no longer, or the bars can no longer be in the same spot, and they can no longer be at the ends, correct? Or if you want to think about this using this exact same model, what we can do is first give each person 1 orange. See, in our stars and bars model, we allow the people to have no oranges, right? So if we were to give each person 1 orange to begin with, then it doesn't matter how we, give them the rest of the oranges. If they don't get any of the rest of the oranges, they at least have 1, right? So if we give each person 5 oranges, or 1 orange, there will be 5 oranges left. So this would be 5 plus 2, so 5 oranges left, plus 2 bars, and we're choosing 2 places for the bars. So this is 7 choose 2, which is 7 times 6 divided by 2, which is 21. That's kind of broken. Broken in what way? You mean the giving each person 1 orange? Hello, welcome to the chat, guys. Feel free to, ask any questions. If you have any like questions you want me to explain, you can send it, or you can DM me on Instagram. Like, good? Yeah. Okay, that's good. Okay, so stars and bars is pretty important. So don't memorize the formula, right? Know what the bars are, know what the stars are, and know how to use this, essentially. Don't memorize the formula. Oh, yeah. this is a good idea, right? Giving each person one thing first for at least type of question. So yeah, as I said, counting is all about models. If you can find a model that works, then literally stick with it, right? Like the hard thing is if you can't find that model that works, you're gonna be stuck doing a bunch of casework, which isn't very fun. But it's yeah, literally all about models. Okay, next thing we'll talk about is counting around a circle. So really, let's say we have like 6 people and we're trying to arrange them around, instead of a line, we're trying to arrange them around a circle this time. So the only difference between arranging them around a circle and a line is that rotations, once again, are considered the same thing, which means rotations don't matter. So pretty much, if we had like 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, these are considered the same, right? So, with this, there's a few ways you can go about this. One way is, you permute all the people first, sit them around a circle, and then you divide by 6 because, there's 6 ways you can rotate them. Like the 1 can be here, it can be here, it can be here. 6 ways in total. Or another, kind of a trick of thinking, or another way of thinking, is you can actually glue a person to the top seat. So for example, right here, I'm going to glue person 1 to this seat. This pretty much gets rid of all problems with rotations, because I'm never going to have person 1 here, right? In that case, I can just rotate this way, and he's up here. And I'm bound to get some sort of duplicate. So, glue one person, or one group, to the top. That's the idea with circular problems. All right. Right, I'll talk about I'll talk about Pascal's triangle first, or Pascal's triangle. Now, there's not too much to say about Pascal's. So some identities are, it's you add the sum, you add the numbers, the 2 numbers above it, and you get the number below. 1, 5, 10, 10, 5, 1. And in general, each of these numbers correspond to a combination. In particular, the ith row, jth thing, j's number is I choose j. So obviously this would be row 0, and the first column is going to be, or the first number is actually the 0th number. You got to, think in that way, where we start with 0. Or you're going to see a lot of things in mathematics where, we start with 0 just because indexing makes it a lot easier. Another thing is, know that these are obviously, in each row, these are the binomial coefficients. I'll go into binomials in just a second. Coefficients. And one more thing I want to talk about is hockey stick. I don't know, but I'm guessing there might be a question on hockey stick. So it's good to know. Although they probably will tell you how to, they'll probably make you prove it before they'll make you use it. But basically, hockey stick just means if you start from any of, like, you know, the edges, and then you start summing up the numbers, then the sum of those numbers, and then you make a turn like this, right? So you know how this kind of looks like a hockey stick. So, or you can go like this way. This way also works, and it doesn't matter where you go. But basically, if you sum the numbers this way, and then you make a turn like a hockey stick, then the numbers on like the stem, or I don't know what this is called on a hockey stick, but it's going to equal the thing down here. That's hockey stick. And if you write this out using combinatorics, it would be like k n choose k plus n plus 1 choose k plus 1 plus n plus 2 choose k plus 2 all the way, let's say, to plus n plus a choose k plus a. This is equal to n plus a plus 1 choose k plus a. So you can see how, you know, we kind of go down this line and then we start here. Or actually, you need to start from n choose 0. My bad. Yeah, you need to start from n choose 0 actually. So n choose 0, n choose 1, n plus 2 choose 2, n plus a choose a. This is going to equal to n plus a plus 1 choose k plus a. Or just a. Sorry. Hello, hello. I love gluing people to table. Yeah, same, honestly. Like, I love gluing them to chairs too. Hello, hello. Hello, Luke Choi. Welcome to the stream. If you have any questions, feel free to ask. You know, if you have any problems, you can send them to me in the chat, or you can send them to me on Instagram. You can send me physics problems as well. Today's just like a Q&A session, really, after I'm done this. Binomial theorem? I won't go too into detail, but I'll just list the theorem here. So basically, a plus b to the power of n equals sigma I from, or let's do I from 0 to n. N choose I, a to the I, b to the n minus I. Binomial theorem. If you want to learn more about the binomial theorem, I have a video. You can go check that out. So I won't go too much in detail here. With probability. Okay. Now with probability, I think we'll just do some problems after this, just to, you know, get a feel for what the questions are like. But with probability, you know, it's desired over total. So probability is pretty much just combinatorics, except you have to find the ones you want, and then you put it over the ones that weren't the ones in total, right? Now with probability, you might ask, should I do combinations or permutations? The truth is, you can actually do both. Combinations or permutations. You can actually do both. The reason is, if you do combinations because you don't care about the order, or if you do permutations and you care about the order, it's going to cancel out since you're dividing it, right? So since it's a probability and it's division, the numbers are going to cancel out. Okay, so I will go over some questions now. If you guys have any problems, you can send them to me. So first problem here. Hold on a second. There you go. Okay, so the barcode strings of a new product are created from 4 letters A, B, C, D, and 10 digits 0, 1, 2, all the way to 9. No 3 of the letters may be written consecutively in a barcode string. There is no restriction on the order in which the numbers can be written. Find the number of different barcode strings that can be created. So, we're given 14 different things. A, B, C, D, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want to, make a barcode with these letters and numbers, but the restriction is no 3 letters can be written consecutively. Right. So with all counting problems, when you see it, big tip here. I'm gonna write it in all caps, but big tip here. Think about the complement. Always think about the complementary. Right? In this case, what is the complement of no 3 letters may be written consecutively? It's 3 letters consecutive or 4 letters, right? What's the opposite of this? Well, it would be what's the normal or the direct approach? No 3 letters may be consecutively. Well, the thing is, you might have a lot more cases, right? You can have all 4 of them separate. You can have two singles and then 1 paired up. And then you also have to deal with, if they're going to be consecutive, they're actually 3 letters together, right? So it's just, and there's also, if you have a pair and another pair, basically it's just a lot of work in different cases. Where if you do 3 letters and 4 letters, it makes it a lot easier with just 2 cases, right? So when you see this problem, first thing you should think of is to use complementary counting. Right. So let's take a crack at this problem. First of all, note that the question put absolutely no restrictions on the numbers, right? Usually, what we want to do is we want to deal with the restrictions first. Because usually dealing with the restrictions first allows for more, allows for freedom at the end, right? But in this case, we actually might not want to do that. The reason is, if we deal with these first, right? If we, let's say, 3 letters and 1 letter, if we group 3 of the letters, let's say A, B, C together, and then D on its own, along with the 10 digits, or 0 to 9, and then we permute them, we're going to get cases where the A, B, C, and D are actually next to each other. And this is kind of annoying because that actually makes 4 letters, and that's going to you know, be the same thing as having 4 letters together. And we don't really want that. Now, some of you guys might be thinking, why can't we just combine these 2 cases, right? If in this case, if we just, you know, put 3 of them together and the other one separate, let's just say A, B, C, and D. A, B, C together, and then D on its own. And then we permute it with 0 to 9. You see that it actually will include cases with the 4 letters. In fact, it will actually include all of them, right? In this case, at least. Obviously, we can change what we group together. But why would this not give the right answer? We have to always, when you're thinking about counting, you need to deal with overcounting or undercounting. This is where undercounting. This is where a good understanding of the model is really important. Can you just not count? Exactly, right? Why can't you just count 4 with the 3, right? The key here is overcounting. Let's say I have a case with A, B, C, D together, right? I have a bunch of numbers before it and a bunch of numbers after it. Not relevant in this case. We're just considering the letters, right? Let's think about how this is going to be counted, or when would this be counted, right? The first time this 4-letter combination would be counted is when ABC is grouped together and D is on its own. That's one time. The other time this is going to be counted is when BCD is grouped together and A is on its own. So this case is actually going to be counted twice if we just use this model here. And that's why this model is going to overcount. And therefore we have to separate the 3s and the 4s. Usually if you're unsure of your model, just separate it, right? Especially in this case where there's only 2 cases, you might as well separate it and, you know, just do separate cases for them. But if you have a good understanding of your model, think about a case where you might either not counted at all, or you're going to overcount. This is where, like, after you create a model, so let's say this was our model, right? After you've created the model, it's important to test the model. So, as I said, right, counting is all about making the model and then seeing if it works. If your model works, like I may not have found a model that you can combine 3 letters and 4 letters, but if you do, and you know, you can show that it's correct, you're not going to overcount or undercount, absolutely, go with that. But in my case, I didn't, so I'm going to do them separately. So, case 1. 1 letter and 3 letters. So, in this case, know that I have to be careful to not put these adjacent to each other, right? Because then that would create a 4-letter, and that's going to overlap with my next case. So before you start, you should have a clear idea of what your cases are going to be. So case 1, 1 letter and 3 letters. First of all, with A, B, C, and D, I'm going to choose one of them to be the 1 letter. So choose 1, right? Then I'm going to permute the other 3 because there's 3 cases for each of them. So this is going to be 3 factorial. I'm going to permute BCD, right? I can have BCD, BDC, so on and so on. So 3 factorial. Then I'm going to permute my 10 digits. So I'm going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's just say this is one of my permutations, right? Then I have an A and I have a BCD that are tied together. And I want to put them into this group of numbers, right? Now, how many places can I put them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 places that I can put them into. And I'm gonna choose 2 of them, right? Now note that I can't, this is different than the stars and bars model. I can't treat these as bars. Why? Because they can't go in the same place, right? If I choose both of them to go in here, that's going to create a consecutive one. And I don't want A and B, C, D to be adjacent. So this is 11, choose 2. Then, note that I have to multiply by another 2 factorial, because let's say I chose this gap and this gap. I can either have A, B, C, D, or B, C, D, and A. So this is kind of the whole process that I go through to find this case, right? So after you can rewatch the stream and go through this logic process again, it's very clear what I'm doing. So make sure you understand how this works, right? Have a clear logic, maybe even before you start. Always think of overcounting, undercounting, that sort of stuff when you're making your model. So yeah, this is different than stars and bars, right? So understanding stars and bars is more important than memorizing the formula. Because one small change and you're going to have to change your entire thing, right? The other case is 4 letters. Now this is 4 letters altogether. This is probably the easier case, right? I don't have to choose a letter. I just have to permute the 4 letters. Then I permute the 10 digits. Or in this case, what I can actually do is I can just treat the 4 letters as one thing and just put it in that group with the 10 numbers and just permute the 11 of them. Right? I can treat A, B, C, D and whatever permutation it has as a number and just calculate it all together with the numbers. So this is just 4 factorial times 11 factorial. I won't do the calculations, but you guys can do it and tell me if I'm wrong, right? I hope I'm not, but I think this should be correct. Questions, chat? Any questions? So if you guys have any problems you want me to explain, you can send it to me. I'm happy to explain any question you guys have. I'll do another one. So another counting one. And yeah, if you guys have any questions, it doesn't have to be on counting. Even physics, for the physics test. I'm happy to answer any of them. Right. Oh, I actually have another question that I kind of want to explain, but we'll go over this one first. Although that other question, the way I did it, might be a bit too unnecessary for the test. Hello, welcome to the stream. If you have any questions, you can send in the chat or you can DM me on Instagram. Happy to answer anything. Alright, so this is a pretty monster question. It is worth a total of, let me see, it is worth a total of 25 questions. It's 25 marks, sorry. 25 marks. So, Jack and John have decided to play a game. They will be rolling a die 7 times. One roll of the die is considered as one round of the game. On each round, John agrees to pay Jack $4 if 1 or 2 is rolled. Jack agrees to pay John $2 if 3, 4, 5, 6 is rolled. And who is paid wins the round. Wait, who is paid wins the round? Oh, geez, that's blurry. Okay. Okay, let's try this again. Okay. Show that. Wait, okay. So one roll of a dice is considered as one round. On each round, John agrees to pay Jack $4 if Jack. Okay. Who is paid wins the round. Okay, so who gets the money wins. That makes sense. In the end, who earns money wins the game. Okay. Show that the probability that Jack wins exactly 2 rounds is 224 over 729. So obviously we're rolling 7 times, right? On each roll, the probability that Jack wins is Jack wins 2 out of the 6 times, right? So the probability of Jack winning is 2 out of 6 or 1/3. So each step is independent, so we can see that this is a binomial problem. So binomial theorem. And in particular, the probability that Jack wins exactly 2 rounds is going to be the second or the third term, right? In the binomial theorem. So that's 7 choose 2 times 1/3 to the power of 2. So he wins 2 of the rounds times 2/3 the probability of John winning the rest of the rounds. Okay, you can calculate this and you should be getting 224 over 729. Alright? Okay, question 2. Explain why the total number of outcomes for the results of the 7 rounds is 128. So 2a, why the total rounds is 128. There's 2 outcomes in each round, 7 times. This is just 128. So this one's not too bad. Part B, expand 1 plus y to the 7 and choose a suitable value of y to prove that 128 equals all that stuff. So 1 plus y to the power of 7 equals, if we just write out using the binomial theorem, equals 1 to the power of 7 plus 7 choose 1, y to the power of 1 plus 7 choose 2, y squared plus 7 choose 3, y cubed plus 7 choose 4, y to the 4, plus 7 choose 5, y to the 5, plus 7 choose 6, y to the 6, plus 7 choose 7, or just 1, y to the 7. Choose a suitable y to prove that it's this. Well, as we can see, this is already pretty close to what this is. Realistically, we're just off by a factor of y in this one, off by a factor of y squared in the second term, or the third term, y cubed in the fourth term. So why don't we just let y equal 1? And then we're done, right? 1 to the power of, or 1 plus 1 to the power of 7, this is 128. So we've proved that all this added up is 128. Give a meaning of the equality above in the context of the 7 rounds. This makes sense, right? The probability of, or not the probability, the context of the 7 rounds. There's one case and another case. One is Jack winning, one is John winning. And since there's 2 cases in each round, then over 7 rounds, that will be 2 to the 7, which is 128. Now, what this means is, let's say Jack wins 0 rounds, then it's 7 choose 0, right? Jack wins 1 round, then there's 7 choose 1 ways. Jack wins 2 rounds, 7 choose 2, so on and so forth. Okay, question 3. Find the expected amount of money earned by each player in the game. 3A. Expected value, right? So Jack wins $4 if a 1 or 2 is rolled. So each round, Jack wins $4 on 2 of the 6 chances. So that is 4 over 3. And John wins $2 on 4 out of the 6 chances, right? So win $2 on 4 out of the 6 rolls, or 4 out of 6 different outcomes. So that is also 4 out of 3. So these are exactly the same amounts. Or, now here's the thing, right? Earned by each player in the game, right? Don't end here. We have to multiply each of these by 7. So the total that they're going to win, we have to multiply by 7. And that's going to be 28 over $3. Part B. Who is expected to win the game? Well, we get the same amount of money, so it should be a tie. Part C. Is this game fair? Yes. Because, no one has an exact advantage. Part 4. So I'll copy the question again. Okay. They have decided to play the game again. Oh boy. Okay, let's try this again. Alright. Find an expression for the probability that John wins 5 rounds on the first 2 games and 2 rounds on the second game. Give your answer in the form 7 choose r squared times blah 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 blah, where the values of r, s, t are to be found. Right. So in the first round, as we've already said, the probability that John wins 5 rounds is 7 choose 5. And John is the one that wins. John is the one that wins 2/3 of the time. So times 2/3 to the power of 5 times 1/3 to the power of 2 times, so on the second round, or the second game, he wins 2 rounds. So that's 7 choose 2. 2/3 to the power of 2 times 1/3 to the power of 5. We can combine this, right? Remember when I said when the sum of these two numbers, they sum to n, or whatever's you're choosing from, these are actually the same thing. So we can write these as 7 choose 2 squared. So 7 choose 5 is the same as 7 choose 2, right? If I'm choosing 5, it's the same as not choosing the 5 or choosing the other 2. Basically choosing the ones that I didn't choose. Times combining coefficient, or combining the powers, 1/3 to the power of 7. And then you can easily find the values of r, s, and t. Now note that we also could have wrote 7 choose 2 as 7 choose 5. So this can also be, r can also be 5 in this case. Now, use your answer in part D to 1 to D1. Okay, so that's part 4, right? And 7 similar expressions to write down the probability that John wins a total of 7 rounds over 2 games as the sum of 8 probabilities. Okay, so this is going to be pretty tedious, but pretty much we can write this as him winning either 1 game, or he wins 0 in the first one, 7 in the second game, or 1 in the first one, 6 in the second, or 2 and 5, 3 and 4. Oh, I'll write it over a bit, but 0, 7, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, 7, 0. And we can write each of these out, right? So we can write each of these out like this. So 0, 7, this is the same, or this is the probability that he wins 0 squared times 2 over 3 to the 7 times 1 over 3 to the 7. And in fact, each of these are going to have the exact same this part. So this just kind of carries down. This is 7 choose 1 squared, 7 choose 2 squared, 7 choose 3 squared, 7 choose 4 squared, 7 choose 5 squared, 7 choose 6 squared, and 7 choose 7 squared. So this way we've found pretty much, the right hand side. We have from 7 choose 0 all the way to 7 choose 7 squared. That's exactly what the sigma is saying. Now we need the left hand side. This is 14 choose 7. So how can we explain that? Well, in this case, right, they're going to play a total of 14 games, correct? And he's going to win, or we want him to win exactly 7 of them. So just like that, we can explain this, right? Out of the 14 games, we predict that he wins exactly 7 of them. And the probability of that is going to be 14 choose 7, and he's going to win 7 of them, so 2 over 3 to the power of 7 times 1 over 3 to the power of 7. Now, since both of our methods are counting the exact same thing, they must be equal, and therefore we've proven this. Now, Jack and John roll a die 12 times. Let A denote the number of rounds Jack wins. The expected value of A can be written as EA equals sigma R equals R from 0 to 12, R times 12 choose R times A to the 12 minus R divided by B to the 12. Okay. Find the value of A and B. So, once again, this is kind of like the binomial theorem, right? So if they roll a die 12 times, then the expected, or then the number of times that they win for each one should be sigma from r equals 0 to 12. 12 choose r, 2/3 to the power of r times 1. Oh, this is Jack, right? So Jack was the one that 1/3 of the time. Okay, so sorry, this is 1/3 to the power of r, right? So Jack wins 1/3 of the games, 2/3 to the power of 12 minus r. So this is the binomial theorem, or how many ways he can win for each one. Now the expected value, we multiply each of these by r, right? So that's the number of ways that he actually, the number of wins that he actually gets. So that's the expected number. Which means if we compare it with this, we can easily find that b equals 3 and a equals 2/3. Differentiate the expansion. So part 2, differentiate the, okay, so we haven't learned calculus, so I'll skip this question. Right. So if you learn calculus, you can give this question a go. But otherwise, yeah, that's it for this question. So not too bad of a question. I personally think this one isn't as tough as the one above, or the one that we just did, as this one. It's not as tough as this one. This one actually had a bunch of counting techniques, and it's very easy to mess up counting, right? Your thinking and your logic and your model has to be very rigorous. You need to really be sure that you're not over counting or anything. All right. Any questions, chat? I'll send this link in the chat once again, so you guys can come on and see it if you want. But yeah, if there's no more questions, any physics questions too? Math, physics questions? Happy to answer anything. Questions, chat? Anything? Anything else you want me to go over? Oh, okay. There's one more question that I want to go over. Although I don't think we will be using it. That is this question right here. Hello, hello. Hello, Cindy. Welcome to the stream. Chat, if you guys have any physics problems as well, feel free to send it. You can DM me on Instagram or you can send it in the chat. Alright, so this question. Sophie and Ella play a game. They each have 5 cards showing Roman numerals IVXLC. Sophie lays her cards face up on the table in order, as shown in the following diagram. Ella shuffles her cards and lays them face down on the table. She then turns them over one by one to see if her card matches with Sophie's 4 card directly above. Sophie wins if no matches occur. Otherwise, Ella wins. So part 1 says, show that the probability that Sophie wins is 11/30. So, in this question, there is one way that you can do it is, obviously you just count it directly, right? The probability that Sophie wins. Well, in this case, it's actually a bit harder to do it directly because it's pretty hard to ensure that no matches occur. But instead, you could ensure that 1 match occurs, or 2 match occurs, or exactly 1 match, exactly 2 match, so on and so forth. So in this case, if you were to do it straightforward, you probably want to use the complement once again. So basically, when you see a counting problem, you always want to think about the complement, right? So the way you want to... Hello, hello. Hello, hello. Welcome to the stream. If you have any physics questions, you can send it to me as well. Yeah, you can send it to me on you can DM me on Instagram or you can send it to me on the chat. So for the complement, we can do oops. Okay, so we can do exactly 1 match, 2 match, 3 match, 4 match, or 5 match. If you want to have exactly 1 matching, the way you can do this is first set 1 number. So let's say I'm going to put I here, right? So I'm going to choose 1 of the 5 numbers and set that. Then, in the remaining 4 cases, now this is the case that's a little bit difficult to actually calculate, but if you do some casework, it's not too bad, right? So let's say we put I here. Then what letter can go here, right? We can't have any more matches because we set this to exactly 1. So we have 3 choices for this one. Then, let's say we put X here, right? For example. Then what letters can go here? V, L, and C, right? Now, if V goes here, then there's only one way to do C and L. But if L goes here, or C goes here, then we can go CV. Or if C goes here, then we can go VL. So in total, there's 3 cases for each of the 3. So there's a total of 9 here. I believe that's correct. Let me just double check real quick. Yep, so there is 9 here, right? In the second case, if there's exactly 2 matching, so which is 1 times 3 times 3, there's exactly 2 matching, let's say IV. So once again, 5 choose 2. Then XLC, they cannot have any the same, therefore it can be LCX or CXL. Only 2 choices here. So times 2. And then for 3 matching, so let's say X is also matching. Well, C and L, there's only one way here. So 5 choose 3 times 1. Plus, if 4 matching, so now 4 matching is actually impossible, right? It's impossible to have exactly 4 matching. So the last case would just be all 5 matching, which is 1. If you add these up, you should get 45 plus 20 plus 10 plus 1. So this should sum up to 76. Now, out of the total of permuting the 5, which is 120, then 120 minus 76, since this is the complement, over 120, this is 44 over 120, which is 11 over 30. Okay, so we got a few question requests. Right. Well, the part 2 is just determining mean of x, variance of x, which isn't too difficult, you know, because this is pretty much just a binomial at that point. Just use the formulas in your booklet. Should be in stats and probability. In a binomial distribution, yeah, just literally use these, right? This isn't too difficult, right? So I'll do them real quick. So mean is NP, so that's 90 times 11 over 30, which is 33. Variance of x, that is NP times 1 minus P, which equals 90 times 11 over 30 times 19 over 30. So this is 3. This is 10. So this is 2. So this is 2. So 20.9, I believe. Yeah, 20.9. Okay. Right, so we got some question requests. It's physics problems though, so let's take a look at this first one. Why do the questions go blurry? I have no idea. Anyways, you can watch the stream again to see what the questions are supposed to look like. Okay, let's take a look at this question. So, a small marble rolls around a horizontal circular path on the inner surface of a conical bowl. The surface of the bowl makes an angle of theta with the vertical. Draw a free body diagram of the forces acting on the marble. So let's say this is the marble, and this is, let's say, the wall. Forces, there is going to be a assuming there's no friction in this case, so this is going to be Fg. This is the normal force. there should be one more force here, right? So this is the normal force, and this is going to be the centripetal force, or centrifugal. Or no, there isn't supposed to be a force here. It's kind of like a... No, yeah. So this is just weight and the normal force. In total, they should make, like, their addition, the vector addition should give this force here. Don't draw this on the diagram, by the way. And that should be the centripetal force. Show that the acceleration of the marble is given by a tangent theta. I'll draw this line a bit better because it's supposed to be more like this. So that if you were to move this down like that, you know, you get exactly this vector here. So theta in this case would be this angle here, right? Show that the acceleration of the marble is given by alpha equals g tangent theta. Well, it might be easier to do it this way. So if we have this line here, then this angle will be theta. And we're pretty much looking for this vector right here. So this vector right here is going to be fg times tangent of theta. So tangent of theta is, or divided by tangent theta. So fg divided by tangent theta. So that's going to be divided by this multiplied by this. So this is just, that's the centripetal force. So Fc equals this. Now we can represent this using acceleration by Newton's second law. The m's cancel out and you're left with this. So the speed of the marble is 1.5 meters per second and its mass is 3.0 grams. The angle of the bowl is theta equals 28 degrees. Calculate the radius of the marble's path. Okay, so okay, so we can relate the centripetal acceleration. So we can, well, realistically, we want to find a relationship between the speed. So we can find a relationship between the speed, the radius, and the centripetal acceleration. And then since we know the mass, we can get g and theta. So realistically, we want v squared over r equals centripetal acceleration. And from, so this is part B, this is part C. So v squared over r equals a. This is equal to g equals g over tangent theta. Oh, so I guess the mass in this case actually doesn't matter, huh? Yeah, I don't think it's going to matter in this case. Right? Because we have, this is the force, or the acceleration, v squared over r equals a, which is g over tangent theta. Yeah, so the mass doesn't actually matter in this case. Rearranging, we get r equals v squared tangent theta over g. So this you can find to be, I'll grab my calculator. 5 squared times tangent 28 times 28 tangent 28 divided by 9.81. This should give the radius of 0.12 meters. The magnitude of the reaction force on the marble from the bowl. So I'm assuming the reaction force is just going to be the normal force then. So now once again, we can make a relationship between the normal force theta and Fg looking at our diagram here. So part 2, we can see that the normal force, which is this one right here, the normal force, this is equal to sine theta, or sine theta times the normal force is going to be the accelerator, or the force of gravity. So this times sine of theta is equal to mg. Okay, so that makes sense. We need the mass to find the reaction force. We don't actually need it to find the radius. Right, so rearranging, we get the normal force is equal to mg over sine theta. So once again, we can find this to be, so 3 grams, 0.003 times 9.81 divided by sine of 28. That is going to give 0.063 newtons. Right, so a small frictional force acts on the marble so that it gradually spirals down the bowl along a path that can be modeled as a circle of slowly decreasing radius. Predict the effect this will have on the angular speed of the marble. Now, we can generally model this. You can think of this as kind of like a satellite going around Earth. We're going to assume that angular momentum does not change much in this case, even though I guess it will, but assuming angular momentum doesn't change, angular momentum is equal to mvr, right? So assuming that angular momentum is held at constant, or it's not going to change much, right? Assuming that it won't change much, so pretty much constant, then mvr, mass, is going to be constant. So this is a constant. Therefore, as r is going to decrease, right, we can see that the speed will increase. Or we can actually, okay, probably makes more sense to write this in the angular way. So this would be mv over r times r times r. And we know that v over r is the angular speed, right? So once again, m is held constant. As r decreases, or as r squared decreases, w will increase. So the angular speed will increase. Okay? Okay, so another rotational mechanics question. A mass on the end of a string is rotating on a frictionless table in circular motion of radius r1 and undergoes an angular displacement of theta in time t. Oh yeah. If you're new to chat, welcome to the stream. Just going over some problems for the test tomorrow. If you have any questions, feel free to ask in the chat, or you can send it to me on Instagram. DM me on Instagram. I'm happy to answer any questions. Okay. A mass on the end of a string is rotating on a frictionless table in circular motion of radius r and undergoes an angular displacement of theta in time t. Okay, the string tension is kept constant, but the angular displacement of the mass is increased to 2 theta in time t. The radius of the motion changes to r2. What is r2? So, the string tension is kept constant. That means the centripetal force stays the same. Now remember, the centripetal force is m, we'll use w this time, w squared r. Right? The reason why I use r is because we're dealing with speeds and angles. That's why I use the angular speed. So this is going to stay constant, right? The angular displacement of the mass is increased to 2 theta. So originally, with R1, originally, the tension, so I'll say T1, this is equal to m times, so the speed is theta over t, right, squared times R1. Now the new tension is m times theta over, or 2 theta over t squared times R2. This is equivalent to 4 times, or this is equivalent to m times theta squared over t squared times 4r2. So therefore, if we compare these two, and since we know that the tension stays the same, r1 must equal 4r2. And therefore, r2 is equal to r1 divided by 4. Did I write this backwards? No. Should be right. Yeah. So R1 divided by 4. Yeah, that makes sense. Right. It's supposed to be 4, right? Yeah, I think I messed up one of the factors somewhere. Hold on. Where did I get the 4r squared? 4r2? I squared this, right? So I get 2 theta. Okay. I think I messed up the factor of 2 here. Hold on. Yeah, from the squared here, right? So you get 4r2. Okay, so I shouldn't be writing it like this, but instead, let's see. Okay, so the thing was this. Did I get the formula wrong? It's supposed to be W squared R, right? Yeah, right? So we have mv squared over r. This is mwr squared over r. Yeah, mw squared r. That makes sense. Yeah, formula is right. So m times, and w is just theta over t. Yeah, answer should be 4r1. It makes sense too, right? When you increase the radius, you should need to go faster to get the same tension. Right? This makes sense. Yeah. No, I think the answer should be A. It should be A. Yeah, the answer should be A. It might seem the other way, but no, it should be A. Yeah, exactly. It should be A. Yeah, so pretty much we can write this as equals m theta squared over t squared times 4r2. So 4r2 equals r1 by comparing the two equations. R2 equals R1 over 4. Right, yeah, I was thinking. Exactly. Think of it in terms of moment of inertia. Yeah, it makes sense. Exactly. All right. If there's no more questions, any more questions? There are no more questions. I gotta go. So. Any more questions, chat? I'll share the link again, so you guys can come on and see the steps once more. So yeah, that's pretty much it. Any more questions, guys? All right. Thanks for coming, guys. That's gonna end the stream here. Thanks for coming, everyone. Appreciate your support. Leave a like if you liked it. Yeah. All right. So yeah, this is gonna be the end of the review. So good luck on your tests tomorrow and on Tuesday. I won't stream tomorrow because then I might be accused of cheating or leaking the questions. So if you have any questions, maybe DM me. But yeah, all right. That's it for today. Thanks for coming, guys.